All right, today I would like to talk to you about some concepts relating to energy, and in particular, something we'll call conservation of mechanical energy. And the word of the day is rhymes. Our friend our friend Lin-Manuel Miranda, author of Hamilton, created many rhymes, and let us create a rhyme of our own, starting with this. You may remember that during our unit on momentum, we imagined pushing on a cart with constant force. We may have actually had Constance the chipmunk push on the cart with constant force. And we said that because there's a force acting on this cart, it will experience an acceleration. And if you compare two time moments when there's constant acceleration, v2 equals v1 plus a times delta t. And please do take notes on this. This is stuff that you're responsible for, and it's one of the larger lectures of this unit. So please do take some notes and leave space in your notes here. v2 equals v1 plus a times delta t. Well, you may recall as I walked through a set of ideas, I did this where I replaced the acceleration with force over mass, which I can do if there's only one force acting on an object. Come on, computer. And then I defined I multiplied both sides by the mass of the cart, mv2 equals mv1 plus f times delta t. Then I just brought the mv1 to the other side, and then I defined this new concept called momentum. The momentum of the cart is the mass of the cart times the velocity of the cart. And so this line just reads that the final momentum of the cart minus the initial momentum of the cart is equal to the amount of force on the cart times the amount of time during which the force was acting. Delta P equals F delta T. A force acting over an amount of time makes an object move faster, changes the object's momentum. And in fact, the force is equal to delta P over delta T. The force is the time rate of change of the amount of momentum that an object has. Well, I could also say this, couldn't I? If we're pushing on a cart with constant force, then v2 squared equals v1 squared plus 2 times a times delta x. And so I could replace a once again with the amount of force I'm applying to this cart divided by the mass. It's just one constant force. What would I do this time? On this equation, I've multiplied both sides by m and divided by 1/2. So I have this expression 1/2 mv2 squared equals 1/2 mv1 squared plus f times delta x. Now move that 1/2 mv1 squared to the other side. And just as I defined momentum over here at this point, now I would like to define k as 1/2 mv squared. And if you know what k stands for, no reason that you should. K, kinetic energy of an object. And so now it looks like the change in the kinetic energy of an object is equal to F delta x. This is not a grand rule of physics. This is only something that is true when one constant force acts on an object, but we are going to have more things to say about changes in kinetic energy. So instead of force acting over time, which is what we focused on in our momentum unit, now we're focusing on force acting over distance. A force acting over distance makes the object move faster, and it changes the object's kinetic energy. Well, you've studied energy in your science classes before, and you know that energy is neither created nor destroyed. So if I or my squirrel is really the thing that's pushing on this cart, right? If the kinetic energy of this cart is changing, where was the energy before? You know that energy can only change forms. It can't be created or destroyed. So where did it come from? Well, energy can transfer between forms, and we've just met the form that we will call kinetic energy. And where was this energy before my muscles put it into the cart, it was in my muscles as chemical potential energy. We'll use the letter U for potential energy, and this little subscript CH denotes chemical potential energy. So we've now met two different types of energy, kinetic energy and chemical potential energy, which is where it was in my body before my body converted the chemical potential energy into kinetic energy of the cart. And just as we had earlier said that force is the time rate of change of momentum, I'm going to use language, English, instead of using math to make this analogous statement. Force causes energy transfer. Force I applied to the cart caused the energy to change from chemical potential energy in my muscles to being kinetic energy in the cart. And force is the rate of change of energy transfer with respect to not time, but displacement. Delta X. Delta X plays the role. Oh, there we go. Delta X plays the role with energy that delta T played with momentum. See, what an elaborate, cool rhyme. All right, well, let's say a little bit more about kinetic energy, energy of motion. The kinetic energy of an object when it is moving is 1/2 m times v squared. 1/2 the mass of an object times the square of the object's velocity. What are the units of kinetic energy? Well, they have to be the units of mass times the square of the unit of velocity. That is kilogram quantity meters per second squared. And indeed, a kilogram meter squared per second squared is a joule of energy. A joule is the unit of energy. And if I had my bell, I would ding it and go, ding, new unit, a joule of energy. That's joule spelled like that. Spelled like that. Well, we had also seen on the previous slide that there was one of the equations that we've written is that the change in an object's kinetic energy is equal to force times displacement. Well, I guess that means that the unit of kinetic energy, a joule, must also be equal to a Newton times a meter. And indeed, yeah, what happens when we take a Newton times a meter? Well, remember, a Newton is a kilogram meter per second squared, so yes, indeed, that times a meter is a kilogram meter per second squared. Sorry, kilogram meter squared per second squared, which is, again, a joule. Is kinetic energy a vector or a scalar? Remember, momentum was a vector, and so an object could have momentum to the left, or an object could have momentum to the right, and if there were two objects that had one of which had momentum to the left and one of which had momentum to the right, they could cancel. Is kinetic energy like that? Well, 1/2 times the mass of an object times the square of the velocity of an object. The square of the velocity of an object is a scalar. When you're talking, it is true that velocity is a vector, but when you're talking about it squared, can't square a direction. We're talking about a scalar quantity. K is a scalar, and K can never be negative. The kinetic energy of an object can never have a negative value. So let's look at an example here. Let's say that I have a 1 kilogram cart going 1 meter per second to the right, and a 1 kilogram cart going 1 meter per second to the left. What is the momentum of this system? What is the kinetic energy of the system? Well, the momentum of the system is this rightward momentum plus this leftward momentum, which cancels. There is no momentum in this system. Is that also true of the kinetic energy? Well, no, because check out what happens mathematically. This negative sign for that velocity gets squared, and so it becomes irrelevant. The kinetic energy of this object is positive. The kinetic energy of this object is positive. It's got some energy of motion. And so the total kinetic energy of both of them together is positive 1 joule. Now let's imagine that instead of pushing a cart, I drop a ball. Right? I gotta use my watch here. Oh, boom. Okay. Well, let's say that I designate some height y equals 0 and let it fall from some initial height y. Well, right the instant before it reaches y equals 0, it's got some downward velocity v. There's some kinetic energy here. Where was the energy before it became kinetic energy? Well, I bet you remember the answer. Energy can take the form of kinetic energy, chemical potential energy, like we saw in my muscles in the first slide, or gravitational potential energy, U, G. U, again, potential energy, G for gravitational. Well, let's get a little bit quantitative. How much gravitational potential energy was there? Well, in the first slide, we had said that if you exert a constant force on the cart, the change in its kinetic energy is the amount of the pushing force times delta x, the displacement through which you push it. Well, an analogous statement here would be that the amount of kinetic energy gained by this dropping object is equal to the gravitational force, not the pushing force, but the gravitational force, times the displacement through which it falls, the displacement that we've called y. So it looks like the amount that this thing changed its kinetic energy is equal to m times g, the mass of the object, times the local gravitational field strength, 9.8 meters per second squared, 9.8 newtons per kilogram, m times g times y, the initial height. The amount of kinetic energy it gained is equal to this amount. So this is the amount of gravitational potential energy it lost. What I'm trying to say is that the amount of gravitational potential energy something has when it has some separation from a gravitating object like Earth, the amount of gravitational potential energy is mass of the object times g times y, where y is the height above whatever we have chosen to call y equals 0. Remember here I said, I've called this y equals 0, and we start at some height y. Y in this expression is whatever we call y equals 0. Let me do some examples. What is the gravitational potential energy of an apple on the table if y equals 0 is the height of the apple itself? Well, there, I guess mgy is m times g times what's the height of this apple above this y equals 0? Well, it's 0, so there's no gravitational potential energy. But what if I have the exact same situation, but instead of calling y equals 0 the height of the table, I call y equals 0 the floor? That would make sense. By the way, this 3-bar equal sign means is defined as. So here I'm proposing to define y equals 0 as the floor. Well, in this situation, if I have a 1 kilogram apple and it's 1 meter off of y equals 0, then it looks like there's 10 joules of gravitational potential energy. So this is maybe a little bit troubling. If I say that y equals 0 is the floor, I say this apple has 10 joules of gravitational potential energy. But if I say y equals 0 is the height of the table, I say that the apple has 0 joules of gravitational potential energy. Is one of them right? Well, it's not really all that much more right to say that the floor is y equals 0 compared with the table. I mean, if we're saying one y equals 0 is better than another, then should we choose the height of the Earth's ground outside? What if we're in a hole? What if we're on a mountain? Is sea level the best? Y equals 0? Well, you could imagine that if this is us in the physics lab and we have this apple 1 meter off of our floor, well, Mr. Arrett will want to say, well, my floor. Mr. Arrett, the chemistry teacher above us, would want to say, my floor is y equals 0, and your apple is actually 4 meters below my floor. How much gravitational potential energy does Mr. Arrett think this apple has? Well, m times g times a y of negative 4 meters. Mr. Arrett thinks that the apple has negative gravitational potential energy. And he is no more right or wrong than the person defining the physics lab floor as 0 is, or the person defining the table height as 0 is. Different origins of position will end up assigning different gravitational potential energies to the same situation. Well, this seems a little bit troubling, but check it out. Let's say the apple falls from the height of the table to the floor. How much was the change in gravitational potential energy if y equals 0 is the table height? Well, initially the apple starts with 0 joules of gravitational potential energy, but then falls to negative 10 joules of gravitational potential energy. Mass of 1 kilogram times g is 10 meters per second squared, times y in this situation is negative 1 meter, so that's minus 10 joules. So I guess according to this, we have a change in gravitational potential energy of final minus initial minus 10 minus 0 joules is minus 10 joules of gravitational potential energy. Well, what if we instead had called y equals 0 the physics lab floor? Then we would have said, well, the apple started with 10 joules of gravitational potential energy, but then ended up with 0. So the change in gravitational potential energy is 0 joules minus 10 joules is minus 10 again. Well, what about Mr. Ehret? What does he think? If the apple falls from 4 meters below his floor, minus 40 joules of gravitational potential energy, to 5 meters below his floor, minus 50 joules of gravitational potential energy, well, Mr. Ehret says that the gravitational potential energy's change is final minus initial. That's minus 50 joules minus negative 40 joules is minus 10. So look, all three of these observers agreed that the change in gravitational potential energy when the apple was lowered by a meter was minus 10 joules. The choice of where to call y equals 0 is arbitrary, and it doesn't matter. Different frames of reference, different choices for y equals 0, will disagree on the amount of gravitational potential energy, but they'll all agree about changes in the gravitational potential energy. So let's take a step back. Let's review. What have we met so far? We've met kinetic energy, that's the energy of motion, and we've met a few different kinds of potential energy, energy of relative position. So there's gravitational potential energy, the relative position of this red ball, if you like, and Earth. When the ball and Earth are relatively stretched, relatively farther apart, there's more gravitational potential energy. We met chemical potential energy, the potential energy that was in my muscles before I converted it to kinetic energy when I pushed the cart. Well, as you remember from biology and chemistry, chemical potential energy takes the form of, among other things, ATP, which is all about the relative position, or I guess energy is released from ATP from chemical potential energy when you lose a phosphate group. So the relative position of that third phosphate group relative to the ADP molecule is what governs the amount of chemical potential energy there. We will talk more later about elastic potential energy, the spring potential energy, the amount of potential energy, the potential energy in a spring that has been stretched from its natural length or compressed from its natural length. But there's elastic potential energy, spring potential energy, depending on the relative position of molecules in the spring. If they're stretched, then their relative position is such that there's more elastic potential energy, and ditto if they're compressed. An object by itself can have no potential energy because potential energy is all about relative position of two objects. If I were in the physics lab, I would show you that demo that I showed you earlier of the bowling ball almost hitting my face. But can't show it to you right now. You'll just have to imagine it. Let me show you this simulation called Energy Skate Park. When I pick up this person and drop him and press play, he goes like this. I don't know if the video is picking this up well. If it's not, search for PHET, that's P-H-E-T, Energy Skate Park, and play around with it, and you can see it on your own computer. If I click the bar graph, I can see the energy changing forms between potential and kinetic energy. And look, I see that total energy stays the same, and this red, this says thermal energy, that seems to be staying the same too. If I go to this tab that says friction, and I turn friction on, and I turn there from none, so there's some friction there. Let me get my energy bar graph up here. I lift him up. I add energy to the system when I lift up the skater. Right now it says all potential. Now look what's happening. There seems to be a slow buildup of thermal energy. And indeed, each time the skater does not go as high. There's still a trade-off between kinetic and potential energy, but it looks like more and more of the total energy is becoming thermal energy. What's going on here? Well, I believe we have just met a different form of energy, an additional form of energy. When you add friction, where does the energy go? It goes into the form of dissipated thermal energy. Dissipated thermal energy, what's going on with thermal energy? It's heat. If you rub your hands together, you feel the heat that comes from friction. And what's really going on there, I think you know from chemistry, is that the molecules in your hands and in the air around your hands are whizzing around a little bit faster. And so really, this thermal energy, this dissipated thermal energy, is really microscopic kinetic energy, but I differentiate it from the large-scale kinetic energy of, say, the person on the skate park ramp or of the bowling ball whizzing through the air, because the person on the skate park ramp can have his energy turn relatively easily into other forms of energy, like gravitational potential energy. But that's not true of the microscopic kinetic energy that's dissipated as heat when friction acts on our hands, say. That energy is sort of out into the air, and it takes something really fancy like an engine to convert that microscopic kinetic energy into other forms of energy. So I differentiate between macroscopic kinetic energy, which is convertible, which is maybe more useful to me. I differentiate that from the microscopic kinetic energy, the dissipated thermal energy. Dissipated is a word that sort of means lost and gone out there. Okay. So, what are some forces that can create dissipated thermal energy? Really, the only ones I know of are friction, air drag, and I guess fluid. A fluid is a liquid or gas. So air drag is an example of fluid drag. Water drag, when something is being dragged through the water, is also an example of fluid drag. The forces that dissipate energy into dissipated thermal energy are called non-conservative forces, for reasons that will become apparent. Forces that don't dissipate energy as thermal energy are called conservative forces. So, for example, the gravitational force. Gravity acting on something doesn't in and of itself create dissipated thermal energy. Neither does the tension force, or the normal force, or the spring force, or the electric force. It's really only friction, air drag, and water drag that are non-conservative forces that we know. I'd like to introduce a new term that's called mechanical energy. The mechanical energy of a system is equal to the kinetic energy in the system plus all the kinds of potential energy in the system. It includes elastic potential energy, spring potential energy in other words, gravitational potential energy, electrical potential energy. These are the types of energy that you can convert between each other. But mechanical energy excludes chemical potential energy, and it excludes dissipated thermal energy, the microscopic kinetic energy. So mechanical energy is pretty much all of the usable forms of energy in a system. It excludes dissipated thermal energy, and it excludes chemical potential energy. The payoff for defining mechanical energy is going to come a little bit later. But let me just look at this right now. Let's say that I start off and I'm holding my cart, and initially it's not moving, and it's at the location that I'm defining as y equals 0. It has 0 gravitational potential energy. How much mechanical energy is there in this system at this moment? And later, once I give it 50 joules of kinetic energy, how much mechanical energy is there in this picture, in the system of the track and the cart and the earth? And then later, after it rises up some amount and has some gravitational potential energy of 25 joules, how much mechanical energy is there in this picture? Well, according to the definition above, here there's no mechanical energy. Here it looks like there's 50 joules of mechanical energy. And here there's 35 joules of mechanical energy. So what happened between picture 1 and picture 2 that increased the mechanical energy of the cart, track, earth system? Well, I put some energy into it. I took some chemical energy from my body and converted it into kinetic energy in this system. So I was sort of an external force that added energy to the system, added mechanical energy to the system, rather. And then what could account for there being a decrease from 50 joules to 35 joules in the mechanical energy between this picture and this picture? Well, I think the only thing that could decrease the mechanical energy of this system would be the action of friction. There is some friction between this cart and this track, and that's what accounts for this lost 15 joules of energy. So friction acted, converting kinetic energy of the cart into dissipated thermal energy and decreasing the mechanical energy of the system. Where am I going with this? When only internal conservative forces act, mechanical energy is conserved. Here, a force external to the cart, earth, track system acted. I acted. I was external to the system. So this external force changed the mechanical energy of the system. Here, this non-conservative force, friction, acted, and that changed the mechanical energy of the system. But if only internal forces that are if only internal forces that are conservative act, then the mechanical energy of a system will be conserved. How is this different from when momentum is conserved? Remember, the momentum of a system is conserved when only internal forces act. There's an additional requirement here for conservation of mechanical energy. That additional requirement is that the forces acting within the system be only conservative forces. So momentum is conserved if only internal forces act in a system. Mechanical energy is conserved in a system if only internal conservative forces act in a system. Okay, so here's a genre of problem, which is a pretty cool one. It's conservation of mechanical energy. It works a lot like conservation of momentum. If I drop a toy moose from a window that's 20 meters above ground, what is its velocity when it's reached 10 meters above ground? Well, you know how to solve this from constant acceleration, but it'll actually go faster if you can use mechanical energy. If you can solve a problem with conservation of mechanical energy, I recommend you do it because it'll go faster. Here's how you draw it. It's very much like conservation of momentum problems. Draw a before and an after cartoon and indicate where you choose to call y equals 0. You have to call y equals 0 the same height in both your before and your after picture, but you can't make a wrong decision as far as where to put y equals 0. Y equals 0 can be anywhere you want. Once you have a before and an after picture, write what kinds of energy there are in each case, write an algebraic expression for each amount of energy, and if internal internal conservative forces act, then you know that the mechanical energy in the before picture must equal the mechanical energy in the after picture, and you can solve algebraically for the unknown. So here's me dropping my toy moose, and I drop it from this height of 20 meters I have chosen to call the ground y equals 0 in this example, but you'll see I wouldn't have to. And so in this picture, I've drawn the moose now with a downward velocity and at a height of 10 meters above the ground. In this picture, I know that the system of the moose and the Earth contains gravitational potential energy. Remember, if you want to talk about gravitational potential energy in a system, Earth must be part of that system. Here, there's gravitational potential energy. Here, there's some gravitational potential energy because the moose isn't at y equals 0, but there's also some kinetic energy because it's moving. So I guess mgy1, that's the initial amount of gravitational potential energy, is equal to mgy2 plus 1/2 times the mass of the toy moose times its velocity squared. I am trying to solve for the final velocity. Divide by the mass. Note that the mass of the moose doesn't matter at all. There I did it. I solved for the final velocity. It's the same solution as I would have gotten with constant acceleration. Okay, substitute in for g and the initial and final heights of the moose, and I find that the moose is falling at 14 meters per second when it's fallen that 10 meters. Okay, could have solved it with constant acceleration, but if you can use conservation of mechanical energy or conservation of momentum to solve a problem, I recommend you do that. One last thought. What if I hadn't chosen to put y equals 0 at the location of the ground? What if there's like this 5-meter hole next to the building and I'm like, oh, well, I want y equals 0 to be at the bottom of that hole? Hopefully this shouldn't mess up the problem. Hopefully an observer standing in this hole would have the same agreement about the final velocity of the moose as an observer standing on the ground. Let's see. The setup of the problem would be exactly the same. Gravitational potential energy plus kinetic energy would be exactly the same up through this line in the previous slide. And let's see, y1 minus y2 would in this case be a height of 25 meters above y equals 0 to a height of 15 meters above y equals 0. And I get the same 14 meters per second. Well, what if I wanted to, what if I were Sherlock and Moriarty at the top of this building and I'm like, oh, well, this is the location I want to call y equals 0. Well, we fall from an initial height of minus 5 meters to a height of minus 15 meters, I believe. Yep. And again, 14 meters per second. So no matter where you put y equals 0, this term y1 minus y2 is the change in height of the moose, and all observers will agree about that change in height. So put y equals 0 wherever you want.